So the question in number 14 is to find a Maclaurin series for the function f of x equals 1 minus cosine of x all over x. Yeah? And just for our sake, let's, in addition to finding a general term for this Maclaurin series, let's also write out the first few terms of it, just so that we have something to plant our feet on. So where do these problems usually start? If you're going to find a Maclaurin series for something, where does that whole process tend to begin? How about right here, in our table of usual suspects? So what does it make the most sense to start with? If I'm going to start with one of these usual suspect series, which one would it be? Cosine of x, naturally, is a good place to start, because it's the only piece of this function which is not just algebraic. I have 1 minus, and I have an x in the denominator, and I can achieve all of that term by term, but cosine of x needs that algebraic representation. So we're going to start in the usual suspect table by plucking out the Maclaurin series for the cosine of x. So let me write that a little bigger. Oops. So the Maclaurin series for cosine of x has as its general term negative 1 to the n times x to the 2n over 2n factorial. And then we're taking the sum as n runs from 0 to infinity. And again, I always like to write out the first few terms so that when we start doing manipulations with these things, it'll be a little bit, I think, clearer to see what's happening to the pattern of the general term if we can see a few of the specific terms as well. So there's the first several terms of cosine of x. Now, according to the order of operations, what step would I do first and what step would I do second in order to get us closer to our final answer? And our final answer is supposed to be 1 minus the cosine of x over x. But there's sort of 2 or 3, depending on your perspective, different things happening here to turn cosine of x into 1 minus cosine of x over x. What should we do first? Subtract 1 minus the whole thing. So we could see that as a single step. I'm actually going to break it into 2 steps. The first step being I'm going to first make cosine of x negative. So just multiply my whole thing by negative 1. If I multiply my whole thing by negative 1, this minus sign we can actually bring inside of the series and turn negative 1 to the n into negative 1 to the n plus 1. And then all that's going to happen is that the signs of my terms are going to reverse. And now here's a Maclaurin series for minus the cosine of x. And then we can just think of it as adding 1 instead of subtracting. And so when I add 1 to that series, I'm just going to write that as, and let me know if this is where you're getting kind of turned around a little bit. I'm going to start by just writing it as 1 plus the sum, minus 1 to the n plus 1, x to the 2n, and then that's divided by 2n factorial, and my sum starts from n equals 0 to infinity. Now we're going to simplify this, but to figure out how that works, let's again look at the first several terms. When I add 1 to my series that I have on the top here, what happens?
0.
Yeah, my first term goes away. So that's what happens. What doesn't happen is anything else. So when I add 1 to this series, all that happens to it is that its first term suddenly disappears, and the rest of the series remains the same. Over 4 factorial plus, and so on. So what that means is that I can actually rewrite this series for 1 minus cosine of x by taking this 1 plus away and taking away its first term. So instead of starting at n equals 0, I can start at n equals 1 now. Again, that's why I like to have the terms explicitly written out over on the right, so that when it comes time to simplify, I have a sense of what I can do to simplify that. So 1 minus cosine x now has the series with the general term negative 1 to the n plus 1 times x to the 2n over 2n factorial. But this 1 that we added to it ended up canceling what used to be its n equals 0 term. So now the new series, we start at n equals 1. That was probably the tricky step on this one. Questions about that so far? So what's my last move to get me from this series to my final answer? What do I need to do to it? Yeah. I just need to divide everything by x. And in classic power series form, whatever we do to the function, we can do to the power series term by term inside of its interval of convergence. So what I end up with here is the sum of minus 1 to the n plus 1 times x to the 2n over 2n factorial. But then I'm dividing the whole thing by x. In other words, I'm multiplying the whole thing by 1 over x, if you like. And again, that sum starts at n equals 1, infinity. Let's write out the first few terms that we can get just by dividing each one of the terms of our previous series by x. So in place of where I used to have x squared over 2 factorial, now what do I have? X over 2 factorial. And x to the 4th over 4 factorial became x to the 3rd over 4 factorial, and so on. And so to finish, I'm just going to simplify this general term that we have sitting down here by reducing my powers of x. If I have 2n powers of x on the top of my fraction and I have a single power of x in the denominator, how much do I have in total? There was a single power of x down here. Yeah. Dividing fractions, the exponents subtract. And there is a formula for the general term of this Maclaurin series. So if we're trying to find the antiderivative for e to the minus x squared in this problem, we're really asking to figure out some way of at least estimating the area underneath this graph. Or I guess in the example that you're looking at for number 47, it's the area from x equals 0 to x equals 1. But what does this curve look like? Yeah, this is exactly, it's proportional to the equation that actually describes the actual bell curve in statistics. It's called the normal distribution. And so the reason that calculus people like questions like this is that this curve is exactly the curve that in statistics describes a normal distribution, which has incredibly broad applications. And finding the area underneath this graph is something that you would do a lot in statistics, because this area would tell you a probability or a proportion. The probability that a normally distributed random variable lies between 0 and 1. The only thing separating this function from the actual normal distribution is a constant factor placed out in front. And the constant factor placed out in front is there to compensate for the fact that the total area under this graph from negative infinity to infinity has to be 100% in order to actually think of this as a probability distribution. So that's just background. That's the background for why we might care about finding an antiderivative for e to the minus x squared, because it can tell us something in statistics about the probability under a normal distribution. But the reason this is an interesting problem for us is that e to the minus x squared, even though it looks like a friendly function, and it is, finding its antiderivative, not so much. Because if we tried to, for instance, make a u substitution, why does this u substitution end up not working? There's nothing to cancel that du with. Right, there's no x that can absorb my minus 2x dx. So u substitution doesn't work. You can try integration by parts all day, and it's just going to make things worse if you try integrating by parts. So the point is that e to the minus x squared is one of these oddball functions. Even though it looks friendly, we can't actually use any technique of analytical calculus that we have to determine an antiderivative for it. As much as we would like to know, we can't do it with the usual toolbox that we have. So we have to resort to series. So out of our list of usual suspects, if we're going to find a series which represents this antiderivative, which series would you like to start with? E to the x is the obvious choice. So picking the e to the x series out of this list, e to the x, whose general term is x to the n. I'm going to write it as 1 over n factorial times x to the n running from 0 to infinity. We need to somehow turn this via a series of steps from e to the x into the antiderivative of e to the minus x squared. So what's the first step you want to do here? That's right. So let's replace the x wherever we see it by minus x squared instead. That algebraic replacement will get us from e to the x to e to the minus x squared. And from there, all we have to do is take an antiderivative. So there's our roadmap for how we're going to do this. Now, replacing x by minus x squared in our power series, actually I forgot to do what I said I always like to do, and that's write out the first few terms. So e to the x is 1 plus x to the 1 over 1 factorial plus x to the 2 over 2 factorial plus x to the 3 over 3 factorial, and so forth. Dot, dot, dot. So when I replace x by minus x squared, my new series is going to start out with 1 still, but then x is going to become minus x squared. X squared is going to become minus x squared, the quantity squared, which is positive x to the 4th over 2 factorial. X to the 3rd is going to become minus x squared, the quantity to the 3rd, which is minus x to the 6th over 3 factorial. So there are the first few terms of e to the x squared's Maclaurin series, e to the minus x squared's Maclaurin series. How do I find its general term? Negative 1 to the n, x to the 2n. And where did that come from? Right, the negative 1 to the n compensates for the alternating feature of this series.
And then the negative x squared times n ends up being, well, just the x squared becomes x to the 2n.
Right, exactly. So we can do this by the book, if you like, just by substituting in our original series that we had negative x squared in place of n. And then to simplify it, to get the power of x by itself, all we need to do from there is distribute this power of n. Distribute it to the x squared, and x squared to the n becomes x to the 2n.
Negative x to the 2n?
Right, so that's the part that people tend to forget. So there's another common place to slip, is that when you distribute this power, not only does the x squared get the power of n, but that negative sign, which is really negative 1 times x squared, also gets the power of n. And so that accounts for the appearance of this negative 1 to the n factor. So that's how we get our general term for e to the minus x squared. Substitute minus x squared in for x, and then x squared becomes x to the 2n when it gets raised to the n, and that minus becomes minus 1 to the n after it gets raised to the n. Now we have a series for e to the minus x squared. So that was the algebra step of getting an algebraic formula for e to the minus x squared. Now here comes the calculus step. What we wanted to do now is take an antiderivative. Well, let's do it first with the specific terms. What's the antiderivative of 1?
Oh, no, it's x.
Antiderivative of x squared? X cubed over 3. Antiderivative of x to the 4th over 2. X to the 5th over 5 times 2, right? I'm going to leave that as 5 times 2 just for fun. Then I'm going to have x to the 7th over 7 times 3 factorial, and so on. So there's the first several terms of this antiderivative. And now to write the general term, what would you like to do? What we really need is we really need to take an antiderivative of this general term of e to the minus x squared with respect to x.
Do we do absolute value, or do you leave the negative one?
We're going to leave that negative. We would take an absolute value later on if we were trying to figure out what was the interval of convergence. When we were applying the ratio test, we would throw some absolute values in, but the negatives are important here because it ensures that when this power series converges, it converges to the value of e to the minus x squared. If we forget about the minus 1s, then we get e to the positive x squared instead, which is not what we wanted. We don't need a substitution for this antiderivative. Let's put the focus, first of all, where the focus belongs. If we're taking an antiderivative with respect to x, then the only term that matters, the only factor that matters here, is the x to the 2n factor. Because everything else, minus 1 to the n and n factorial, those are functions of n and not x, and so with respect to the integral that we're taking, they're just constants. So the minus 1 to the n and the n factorial, those are just going to come along for the ride. Minus 1 to the n over n factorial. And now all I need is to take the antiderivative of x to the 2n. And when you take the antiderivative of x to the 2n, what's the first thing you do? Raise the exponent by 1, and then divide by the new exponent. And that's all there is to it. Again, this is the great thing about power series. This is the sales pitch, is that the antiderivative that we just did was really the first antiderivative that you ever learned how to do in calculus, the antiderivative of a power of x. Nothing could be more straightforward as far as antiderivatives go. But trying to do the antiderivative of e to the minus x squared as the whole function over here, not only is that difficult, it's impossible to do analytically. So finding a power series for this antiderivative is the only recourse that we have if we want to understand what the values of the antiderivative of e to the minus x squared are. And if you take a course in probability and statistics where you have to compute normal probabilities of a normal distribution, because there's no analytical formula for them, you end up using these tables of data and statistics and all these numbers, they call them z-score tables, that tell you the values of this function, this power series in other words, for various values of x.